All right, our next speaker is Nick Silverman, who's a hydrologist at the University of Montana, and his research focuses on the interactions between water, plants, and climate at broad scales. Please help me welcome Nick.
Good morning, everybody. I'm going to get out of the uplands and get down into the valley bottoms a little bit, talk about riparian and mesic restoration. Over the last year or so, we've been developing a tool that helps to evaluate, target, and monitor these restoration efforts, and I'm going to kind of walk through how we got to where we are today. So to do that, I'm going to start a year ago. So this was a presentation that I gave at SRM in 2018 in Reno. Subsequently, it was turned into a publication, but it was focused on just looking at the efficacy of mesic and riparian restoration based on low-tech and process-based methods across the West. And there's I want to read to you a quote from our conclusions in that paper. It starts with, it might be beneficial to consider designing restoration projects in concert with remote sensing methods, because by doing so, we'll be forced to develop restoration approaches that are affordable enough to scale to the extent of the ecosystem degradation, creating change that is detectable at landscape scales, and monitoring these changes over a time period to show ecosystem-level response. And so I think what's important here is that this is sort of a co-benefit of using these broad-scale satellite remote sensing technologies, is that if we think about our restoration projects from the beginning as needing to be seen by space, then we can start thinking about these projects at perhaps the level in which they're really working, so these ecosystem level responses. So by developing this tool, in a sense, hopefully if we can use this from the beginning, we're thinking about things at the right scale. So last year, and in that paper, we took a look at 3 projects around the West. The first one was in Gunnison, Colorado. This was a project where Bill Zedike installed many of his different structures in several different locations, several different watersheds, mainly in small, ephemeral, intermittent stream systems. Over 500 of these structures were installed. It started back in 2012 and then has proceeded subsequently since. And what we found using NDVI and looking at pre- and post-restoration was about a 24% increase in NDVI. And I'll interchange NDVI and productivity, even though I know they're not the same thing, as Stan just pointed out to us. But here we're sort of using NDVI as just a proxy for productivity. Then we also looked at another project over in Oregon. This is on Bridge Creek, which is a perennial stream system. Here, beaver dam analogs were installed back in 2009. 120 of these beaver dam analogs were initially installed. Later, Beaver came back in and installed another 120 to complement that. And so we're looking at the full response of this project. And again, we saw about a 20% increase pre to post restoration. And then finally, we looked at Maggie Creek. Maggie Creek is mainly a grazing management project that started back in the 1990s. And it was really a whole-scale watershed plan. So we're really looking at a big wholesale change in how the land was managed. And here, since we had enough time, almost 20 years since restoration, we could look at something that we're calling vegetation sensitivity. And I'm going to talk a lot about that in this talk, but this is the first time that we used it in the paper that I showed. And essentially, this sensitivity is the amount of change in NDVI per change in precipitation in this case, or in water or some sort of water metric. And you can see here in the years since restoration that sensitivity has dropped almost exponentially up until the present time where it's flattened out. So we weren't the only ones thinking about evaluating restoration projects using Landsat imagery and specifically even vegetation sensitivity last year. So this was another paper that came out last year by Hausner et al. And they used a similar metric here. On the y-axis is NDVI, and on the x-axis is precipitation. And each one of those points is a year. And you can see there's a difference in the slope of that relationship between the pre and post restoration. The pre-restoration are the white dots. The post-restoration are the dark black dots. And so I'm calling that slope sensitivity. So essentially that's the response of vegetation to water. And you can see after the restoration effort, you have less sensitivity or that slope is flattened out. Okay, so that's a lot about what happened last year, and we learned a lot, and we wanted to take all that information on these different projects and how we evaluated them, and think about how we could create a tool to make this more accessible to the land manager and practitioner so they can do these same sorts of analysis both pre and post restoration. And so we really broke it down to 3 different tools that are needed. One is something to evaluate the landscape, the whole landscape for patterns of hydrologic resiliency and stress. Then we really want something to target these areas that are perhaps particularly sensitive to drought or water. And then finally, we want to be able to monitor these areas over time and also look at how our restoration has worked or not worked over long time scales. So we went back to that vegetation sensitivity that both we developed for the Maggie Creek project and then also was subsequently used in the Hauser et al. Paper. And we said, okay, there's something here because essentially this is really connecting the dots between vegetation and water. And if we can decrease sensitivity over time with our restoration efforts, essentially we're storing more water so that in drought years things can stay green longer. And that's a good thing. So we thought we'd start with that metric. And essentially, if you break that down, you can think there's really 3 scenarios when you're looking at this vegetation sensitivity. The first one is this flat relationship with high NDVI. And we would say this is a low sensitivity because it's green all the time. There's great hydrologic connectivity here. And then we have another scenario with the exact same sensitivity, the exact same slope, the relationship is the same, but in this case, it's brown all the time. And what we're saying is, in either one of these cases, we're not so interested, because either there's great hydrologic connectivity, and maybe, so this is probably not an area we need to dive into and take a look at, or there's no hydrologic connectivity, there probably never was, and our efforts would be meaningless. So it's this other case here that we're most interested in, and this is the case where there's a strong relationship between NDVI and water. And I should say the x-axis here, and I'm going to talk more about this, this is the climactic water deficit. Before we were using precipitation, we're using a different metric I'm going to go into in a second. But essentially just think about it as a drought metric for now. And so this last case here, this is where in wet years we're getting green up, and in dry years we're not. And so that's saying there is some sort of hydrologic connectivity, but it's not always there, or we're not storing water year to year, or throughout the season. And so this might be an area to go onto the ground and take a closer look at. Okay, so now this climactic water deficit. Again, you can think about this as sort of a metric of drought, but essentially it's very simple. It's just the difference between the potential evapotranspiration, so this is the energy that's in the atmosphere to evapotranspire, and then the actual evapotranspiration, which is driven by the water supply. And so it's just this difference here between the two. This is essentially the extent of the water limitation, and it's more or less a measure of drought. The advantage to this over just using precipitation is we're now combining both precipitation and the phase of energy. Obviously, we know water on the landscape is a combination of both how much water we get and then how quickly it evaporates. This accommodates both of those. Okay, so the other thing we have to do here is we have to figure out a way to map the riparian areas at large scales. And we use this method by Nagel et al., which I won't go into a lot, but there's a whole paper on it. I wouldn't say we use it exactly, but we sort of base it off of it, and it's this cumulative cost algorithm that takes into the slope of the from a DEM and then the stream center line. So it's solely based on elevation. And I kind of randomly picked a place in Utah here to walk through how this, how the development of this tool works. So here we have the National Hydrography data set stream center lines. And from here we get the longitudinal reach boundaries. So we just use the reaches that are defined in the NHD, and then we use a DEM, and we use this cumulative cost algorithm to then get a lateral width to this to these riparian areas. So the NHD provides the longitudinal stream reach, and then we use this algorithm to get a lateral mapping of the valley bottoms or riparian area. The colors here are just showing that the different reaches. They don't mean anything, but you can see that that we get we capture the floodplain decently well. And then we calculate this vegetation sensitivity that I talked about across the entire landscape. And again, this is that relationship or the slope of the line between NDVI and the climactic water deficit. And we do this for each pixel through time using Landsat imagery, so 30-meter resolution. And here you can see that the red areas are areas that show up as high sensitivity or a steep slope, and the blue areas are flatter, a flatter relationship or low sensitivity. And then we can take the mapped riparian areas and we just calculate the average sensitivity across those areas. And so you can see there's some variability here among these different stream reaches. The warmer colors representing higher sensitivity, and the cooler colors, again, a lower sensitivity. Okay, so that's kind of how this riparian sensitivity index is developed. So I want to talk a little bit now about how you might be able to use this. So first, just evaluation. We can use this, we can look at really broad scales. This is across the entire West here. You can see big, broad changes and sensitivity across the landscape, the high plains being really sensitive, the coastal areas being less sensitive. And then we can zoom in. So this is just a watershed just south of us, the Bitterroot watershed in Montana. And we can zoom into there, and you can see this is all broken up by stream reaches. And it's hard to tell, but essentially you can start to get some watershed patterns in here where this area, these are the Sapphire Mountains, this is more rangeland. You can see mainly red through here, high sensitivity. Over here, this is kind of our water tower in the area. This is the Bitterroot Mountains. They're steep, they collect a lot of water and snow, and they stay pretty green. So you can see those areas are less sensitive, and then our valley bottom is kind of a mix because this is where we've got agriculture and different irrigation practices and all sorts of stuff. So, but anyways, the point is you can start to get, just evaluate your watershed that you're working in to start to understand sort of the vegetation sensitivities within it. We can also use this to target areas. So we'll go back to that random area in Utah here, and we can say, okay, well, this is the overall sensitivity of the vegetation to water. But what if we just looked at a polygon? And you can draw this polygon however you want. And we say, okay, within this polygon, rank the sensitivity. So essentially standardize it across space here. And then you can start to see some things pop out a little bit more where some of these reaches, at least for the area, are pretty low sensitivity. So in other words, they're either always staying green or always brown. And then other areas are changing quite a bit. So if we wanted to zoom in on this, this lower reach here, this red area of high sensitivity, we can also draw a polygon around that, and we say, okay, well, how has this sensitivity changed over time? Okay, yeah, its average is high sensitivity, but let's take a look at what's going on over time. We can plot that, and you can see, and again, I just kind of picked this fairly randomly here, but kind of an interesting case, because here we show this as one of the higher sensitivities in the area, but actually the sensitivity is dropping over the last 5 or 10 years. So this might tell us that either something, it's restoring itself, something's going on here, maybe this isn't such a great area. So the point is that it's really important to look at both the space and time component of these areas. Okay, so now I want to circle back to these projects that I started off with. That we know some intervention has occurred, some restoration has taken place, and see how they look on that from a monitoring perspective using this tool. So this is Gunnison. Again, this is the restoration using the Z-dike structures that started back in 2012. And this is what that looks like over time. So there's lots of lines because in Gunnison there were lots of different stream reaches. So these are all of the stream reaches in which some sort of restoration or rehabilitation was implemented. And you can see if I draw that line right at 2012, something really interesting happened. That sensitivity dropped. So we're picking that up. Also, something really interesting not related to the restoration is that drop around 2005. And I've talked to some of the folks there who are in the area, and our best guess at what's going on there is in 2002 there was a major drought in the area. And after that, it stayed pretty dry for subsequent years after. And so my best guess is this is picking up sort of a decrease in sensitivity. Essentially, you're lowering the bathtub of water, or that natural storage. And then in 2005, there was a big rain event, a really wet year, and that sort of refilled it back up, brought it back up to another, back up to its equilibrium state. So anyway, so some other really interesting things you can pick up when you look at this over time. Bridge Creek, this is where those beaver dam analogs were implemented back in 2009. And here, if you look at one of the areas, again, you can see if you draw a line where the restoration began, you see an immediate response. Sort of interesting, it jumps back up afterwards. I don't know if that's exactly what's causing that rebound, but it jumps back up to a lower sensitivity than it was previously. And then finally, we can look at Maggie Creek. This is the grazing management project that took place over 20 years ago. And here, if we just look at the overall trend here, there's some bumps along the way, but the overall trend and sensitivity, you see a sharp decreasing trend in that sensitivity. So it seems to be picking up these restoration projects fairly well, and then hopefully also you've seen some ways to use it pre-restoration to help target and evaluate the area. So in summary, we've developed some tools to evaluate, target, and monitor mesic and riparian restoration projects around the western United States. A co-benefit of using these tools is that it focuses us to think and work at larger spatial scales, better aligning our efforts with the ecological processes we're trying to restore. Our goal here is to empower land managers and restoration practitioners to explore ways to build resilience using low-tech, process-based restoration methods. And again, these tools, the plan is for them to be freely available in the near future on the Rangelands analysis platform. Thanks a lot.